Time for us to do some practice involving changing the order of integration for multivariable integrals. Now, it's kind of a fun process, and really what it boils down to is, can you see the shapes? And can you describe the shapes? Really, it's a lot about geometry. And so we're really going to start to flex our geometrical intuition. And we're going to get a lot better as we go on, especially when we get up to triple integrals. Well, that's a foreshadow of things to come. Now, the way we get better, of course, is through practice. Practice as much as you can. If you're following along with the video, see a problem you like, use the pause button. Try it yourself first. See how far you can get. With practice, you'll see, aha, you're getting pretty good at it. And then you're getting pretty amazing at it. And then you can start to teach me. And that'll be wonderful. Look forward to it. Well, let's begin. First problem. Find the integral 0 to 1, integral x squared to root x squared plus y squared dy dx. Now, this one's not really a changing order of integration, but it's getting used to us saying, hey, you can have functions in the bound. So we want to get used to that process because it will show up as we go along. So we're just going to do what it tells us to do. And you'll see it says, look, it's a double integral. So you integrate twice and you do it one layer at a time. Work from the inside out. So the inner part, that's this integral with respect to y. So we say, okay, this would be the integral 0 to 1. And when we integrate this with respect to y, treat x like the variable, well, that would be x squared y plus 1/3 y cubed. And then we're evaluating, and remember these bounds are associated with y. So when we say x squared here, we really mean y equals x squared. And similar, y equals square root of x. All right, so those are the bounds that we have to evaluate at. All right, so plug those in. So where we see y, we put in square root of x. Now you can also think of square root of x as x to the half power. That's a more calculus-friendly way to think of square root of x. So I have x squared times x to the half. So if we put those together, that would be x to the 5 halves. Then we have 1/3 times square root of x cubed. Well, that's x to the 1/2 to the power 3. So that would be 1/3 x to the 3 halves. All right. So that's when we plug in square root of x, subtract, plug in x squared. X squared times x squared, x to the 4th. And then x squared cubed, well, that would be x to the 6th. So plus 1/3 x to the 6th. And there we go. One layer down, one to go. So the next layer, well, we integrate with respect to x. X to the 5 halves, integrate that. You'll get x to the 7 halves and then multiply by the reciprocal, 2 7s. Here, we'll have the 1/3. Then we're going to have x to the 5 halves, which is what you get when you add 1 to 3 halves, and multiply that by 2 5ths. Minus, all right, this will be x to the 5th, multiplied by 1/5, and minus again, because notice this minus distributes through. So minus 1/3, and here will be x to the 7th times a 7th in the front. And we're going to evaluate 0 to 1. I don't need to write down x equals 0, x equals 1 here because there's no ambiguity. When there is ambiguity, it's useful to write it down just so you don't accidentally evaluate the wrong thing. Not that that would ever happen. It kind of has happened sometimes to me, so but it's better to be safe than sorry. Now, the good news is plugging from 0 to 1, very easy. When you plug in 0, 0, 0, 0, plug in 1, well, you get the coefficients, because 1 to any power is 1. So 2 7ths plus 2 15ths minus here 1/5 and minus 1 over 21. Now, if you really wanted to, you could say, well, common denominator would be 105. So what would you end up with? Well, by the way, why do we say 105? 105 is really 3 times 5 times 7. So to get from 7 to 105, you'd multiply by 15. So that would be 30. To get to 15 to 105, you multiply by 7. So 14. So to get from 5 to 105, multiply by 21. So subtract 21. And to get to 21 to 105, multiply by 5. Subtract 5. So what do you have here? You have 30 plus 14, 44. Minus 21 and 5, that's minus 26. 44, subtract 26, leaves us with what? Well, leaves us with 18. So you have 18 over 105. And, well, okay, good news. 18 over 105, they have a common factor of 3. So we can pull that out. So what happens? Well, we'll have 6 downstairs, 35. So there we go. Final answer. 6/35. All right, good. Now this is just getting us used to the idea, integrate one layer at a time. It's okay to have functions in the bounds. Just proceed like you normally would. And essentially don't panic when you have functions in the bounds and you're doing your iterated integration. Once you get to the integration part, it should be a somewhat mechanical process, assuming, of course, we can find antiderivatives. The functions we're going to mostly consider here will basically essentially be almost always guaranteed to find antiderivatives because we're not trying to test you on finding antiderivatives. The main thing we're working on is learning to set up the bounds. All right. Well, more to do, right? Oh, yeah. There'll be more problems. So, sketch the regions associated with the following integrals. So, in other words, we're thinking about we're integrating over some region in the plane a function. We don't care what the function is here, so it's just f of x, y. And so we have to think about, okay, how do we figure this out? Now, the way we do it, we'll do them both, is to say, look, the regions are being described by the bounds. And so we have to learn how do we translate from the bounds to the region. And eventually we'll also have to go from how do we get from the region to the bounds. We want to be able to jump back and forth. So in some sense, if you have the bounds, getting the region is not so bad. What you do is you remember, look, there's association. So that the outermost integral is associated with, like, in this case, the dx, and the innermost is with the dy. So here, it's saying what? We're going from 0 to 2. But more particularly, we're going from x equals 0 to x equals 2. That's what the outer integral tells us. The inner integral, that's a y. And that tells us we go from y equals 0 up to y equals x squared. So from the bounds, we get a series of inequalities. Now that's not a sketch, but it's describing our region by inequalities. So the next thing to do is do our quick sketch here. And what do we see? Well, we see y equals x squared. Okay, and we're only going between 0 and 2. So here we go. There's y equals x squared. And we're going x equals 0 to x equals 2. So we can mark here's x equals 0. And over here is x equals 2. And we're going from y equals 0, which is down here, it's the x-axis, up to the line y equals x squared. So essentially, you should think of it as we're doing it this way. So for any value of x, I'm going to go from 0 up to x squared. So we're slicing, in some sense, in a nice vertical fashion. Well, okay, we're halfway done. And see, it doesn't feel like we had to do too much, because once you get the hang of, like, the bounds are describing the region, just read it off, and it's like, hey, this isn't so bad. We should have been doing this a long time ago. This can be kind of fun. All right, well, next layer. What do we have? Here, outermost goes with y. So we're told y goes from 0 to 4. So the outermost layer is always between numbers. Keep that in mind. If you set something up and the outermost integral is not between numbers, something has happened and you need to go back and see what you did. The innermost layer is associated with x, and go from x is square root of y all the way up to x equals 2. Okay, so, what would that look like? Now, that would look something like the following. Well, x equals 2, that's actually pretty easy to draw. Now, what does x equal 2 look like? It's just a straight vertical line. So, okay, so we have x equals 2. Now, well, how about this? X equals square root of y. Well, we know y equals square root of x. We know that shape. So if we talk about x equals square root of y, it's essentially a flip of that. And, okay, so that would look like what? Well, it would look like this curve here. So x equals square root of y. And now we have, here we go. This is at 4. And you can see what's happening. For every value of y, we're say start at x at square root of y and go over to 2. So we're doing this. So it's like we're doing horizontal slicing. Now, we're done with the problem, but I think that they're trying to hint at something. So let's use this as a learning opportunity. What do you see about these two shapes, other than the fact that I'm not a great artist? What's going on here? It's they're the same. And so, wow, cool. Now, you might say, wait, how do we know that? Well, notice, if y equals x squared, that's the same as x equals square root of y. So it's really the same bounding curve. And so, what's the difference? Well, the difference is the order of integration, how we're thinking about breaking things up in terms of slicing. Now, one other thing. Okay, so sure, we can change order of integration, and that's great. But notice the bounds. See, when we do only rectangles, if you swap, super, super easy. Whoop. But we're not doing a rectangle here. And notice that when we swapped, the bounds looked markedly different, very different. And so when you're integrating over a region that's not a rectangle, it's not just as easy, I'll just switch the bounds. No. Work lies ahead. It's not bad work. We're not going to be afraid of it, but it's work. And so we want to make sure we do the process. We carry it through, and we're careful. We really want to be careful, right? All right. Well, good. So let's keep going. More to do, right? Oh, yeah, more to do. So, change the order of integration for the following integral. So, integral from -1 to 0, integral negative square root of y plus 1 to positive square root of y plus 1, f of xy dx dy. So, notice we're not going to be able to do the integral because you don't know what f is. So, this really is about changing the order of integration. Straightforward, this is what we were here for today. We're like, this is why we came today. This is our meat and potatoes, so to speak. We really want to get into this. So, we start thinking, okay, what's going on? So, just remember that the bounds are describing our region. So the first step is take your bounds and turn it into inequalities that describe our region. So we're told y goes from -1 up to 0. That's the outermost integral. It's associated with y. And x goes from minus square root of y plus 1 and all the way up to positive square root of y plus 1. Now, we look at these curves. They're kind of strange, right? So x equals square root of y plus 1. Plus or minus, doesn't really matter. If we were to graph it, how would we go about it? Well, one way we could do it is we get rid of the square root. So you could say that's x squared equals y plus 1. Or we could say, hey, that's y is x squared minus 1. Oh, okay. All right, I'm feeling pretty optimistic here. So what do we see? What do we see? Well, what we have is if we sketch this y equals x squared minus 1. Sorry, it's a parabola. I'm going to do it with the dotted line for right now, just so we can fill in the parts that we need to. Okay, so we have our parabola. So here's our y equals x squared minus 1. we should try to understand where does the pieces x equals square root of y plus 1 fit in, and what about x equals minus square root of y plus 1? Well, x equals positive square root of y plus 1, that will be on the right-hand side. So this is x equals positive square root of y plus 1. In some sense, you can see, oh, yeah, because we're taking the positive square root, x should be a positive value. All right, that makes sense. On the other hand, the negative would correspond to the left-hand side. So this would be x equals minus square root of y plus 1. And finally, we say, okay, well, where are we going between, right? Where are our bounds from? From where to where? Well, we're going from -1 to 0. Now 0, that's up here. This is y equals 0. And -1, well look, y equals x squared minus 1. -1 would be right here at the very bottom. So currently, the idea says, as you go from -1 to 0, you're going to go from minus square root of y plus 1 to positive square root of y plus 1. So our region is sort of this bottom piece of the parabola. So now we have our parabola. We've sketched it. We see what our region looks like. And we say, wow, beautiful, beautiful. This is something we can work with. So where do we go? Well, we say, hey, what we're going to do is we're going to switch the order of integration. If we were doing our horizontal slicing, that means we're going to switch to vertical slicing. And what we need to do is figure out, all right, what happens to the bounds? So let's think about our various bounds. Okay, suppose we work from the outside in. I like to work from the outside in. So we know we need to end up with an integral. Then there's going to be f of xy dy dx. So we start with, what can we say about x? Well, we got to figure out, where do we go from where to where? Well, that's where x squared minus 1 hits y equals 0. Well, that's where x squared equals 1, which means we're going from -1 to positive 1. So -1 to positive 1. Now, what about y? Well, we're going from the parabola on the bottom up to this axis, which is 0. So we're going up to 0, and then our parabola, well, what's our parabola? Our parabola is y equals x squared minus 1. So we're going x squared minus 1 up to 0. And that's it. We're done. So really what happens is, from the picture, we could have said, all right, we want to get x, y, and we look and say, hey, we go -1 to positive 1, and then we say, where does y go? It goes x squared minus 1 up to 0. Now, one small note, and we'll see this in other problems, but I want to just emphasize, we did take advantage of the fact that for this particular shape, when we cut things up, we only had to have one description. In other words, when we look at it in terms of the horizontal slicing, there was a consistent left and right side. When we looked in terms of the vertical slicing, there was a consistent top and bottom side. If you ever have a region where you say, oh, I have a transition, so the way I describe a side goes from one curve to a different curve, you have to make sure to break it up. And so be prepared that it's possible that you might have to break things up. It's also possible, by changing order of integration, that you can put things together. We'll see some examples as we go on. All right, well, good. Let's keep going. Next problem. Find the following integral by first changing the order of integration. You're like, what? Why should we change the order of integration? Let's just do it. And we look at it, integral of e to the y squared dy. No, let's not do that. Because we can't. We don't have the technology. So we don't have the tools needed to carry out this integral. So we need to think about, okay, is it hopeless? And we say, well, wait, and let's understand our motivation. Why do we want to switch? we can't integrate this with respect to y. That's 100% true. We can integrate it with respect to x because there is no x. So in terms of x, it's a constant. So we say, hey, we are having a hard time starting this if we integrate it in the current order, but if we were to switch the order of integration, we can at least make some progress. So that's a signal that says, hey, there's a reason why we're changing the order of integration. Not just because, they ask us to, but because that's a way that we can make some progress. All right, so let's start. We got to think of our bounds here. So we say what? Well, x goes from 0 up to 4. That's the outer integral. And 1/2 x up to y up to 2. So reading off the bounds, now we have a description of our region using inequalities. Well, okay, so we've got to draw our picture, get a sense of what's going on here. Okay, so, well, the only real curve we should worry about is y equals 1/2 x. Okay, that's not hard to draw. That's the slope, goes to the origin, it's a line, has a slope of 1/2. So, okay, so it does something like this. So there's the line y equals 1/2 x. Okay, and then we'll have y equals 2. Let's say it's this line. Here's y equals 2. And on a side note, where does 2 and 1/2 x intersect? Well, very conveniently at 4, which is not too surprising because we have a bound from 0 to 4. All right, so the current setup says, all right, we're integrating in the order dy dx. So x goes from 0 to 4, so I'm going between 0 to 4. And for any value of x, excuse me, I'm going to go from 1/2 x up to 2. So what we get is this little triangle. That's our area. That's the region we're integrating over. Great. Well, now what we need to do is to turn this into an integral in the opposite order. So we should mark a couple things. What should we mark? Well, we should mark our curves. We have this curve, which we didn't mark, the y-axis, that's x equals 0. And this line, y equals 1/2 x, we did mark it, but we wrote it as y as a function of x. We want to translate as x as a function of y. Well, here it's not so bad. That becomes x equals 2y. And now we're thinking, great, when we change the order of integration, what's going to happen? Well, we're going to get the integral, and still the same function because the function doesn't change, dx dy. So we have to start thinking, where does y go from? Well, okay, looking at our picture, we say, okay, what's the smallest value of y to the largest value of y? Well, we can read that off. We're going from 0 up to 2. All right, that's not so bad. Now, for a fixed value of y, because what's happening on the inner integral is we're saying, okay, we have y fixed. Where does x go from? So the picture says what? Well, we're going to go from left to right. So in other words, we're doing our horizontal slicing. So the left, 0. The right, 2y. Okay, good. So go 0 up to 2y. All right, well, great. And now, hey, this is wonderful. We can actually do one layer. Because integrating with respect to x, as we said, not so bad at all. E to the y squared times x, because e to the y squared acts as a constant. Evaluate that, x equals 0 to x equals 2y dy. All right, plug in 0, you get 0. So what do we end up with? We get 0 to 2, e to the y squared times 2y dy. What? That's beautiful. That's gorgeous. What do you see? We can make a substitution. U equals y squared. du equals 2y dy. So that this would become the integral, well, updating our bounds, 0 squared to 2 squared, so 0 to 4, e to the u du, which is e to the u, evaluated from 0 to 4, which becomes e to the 4th minus e to the 0, which is 1. And we're done. Wow. Wow. That's beautiful. That we found an answer is beautiful, but the answer itself is so nice. Extra beauty. Wow, this is fun. And so this becomes one of those fun things where it's like, hey, by changing the order of integration, we can actually make progress in impossible integrals. It's always fun to make progress. 4 out of 5 dentists recommend it. All right, well, let's keep going. On to our next problem. All right. Find the integral over a region 2 over 1 plus x squared dA. Ooh, arctangent, right? Where R is the triangular region. Oh, it's a triangle. Okay, let's draw this. Vertices are at 0, 0, 2, 0, and 2, 2. Okay, let's mark where these vertices are. So 0, 0, 2, 0, and 2, 2. Okay, so there's our triangle. All right, great. Now, it didn't tell us which order to integrate in, which means what? Which means we get to set it up. And so we get a choice. So we have to choose. Now, looking at the function, it's easy to integrate with respect to y, and it's not so bad to integrate with respect to x. I would probably say it's easier with respect to y. Okay, so maybe we're biased towards dy dx. But before we do that, let's note one other thing. Take a look at our picture here. Now, if I have a triangle, I can think of integrating the order dx dy comes down to saying let's compare vertical slicing versus horizontal slicing. So vertical slicing would look something like that as we go from the top curve to the bottom curve. Horizontal slicing would look something like that, left curve to the right curve. And now the curves themselves, we can mark down what they are. It's pretty straightforward. Down here, this would be y equals 0. Over here, x equals 2. And over here is y equals x. Now, I claim that if you have no other information than this picture, that you should be biased towards one of these two options. Should we prefer the vertical or the horizontal? And why is the answer we prefer the vertical? Yes, we should prefer the vertical here. And there is a compelling reason. Now, I'm not saying this will always be true, but there is something going for vertical that really makes us go like, woo, we like that. What does vertical have going for it? Notice the curves that you're going between. 0 to x. Okay, that's not so bad. Here, you'd be going from y to 2. Now, the reason I say y here is I have to say, well, think of this as functions of y. Here, when we do vertical, it's functions of x. The thing is that the vertical slicing uses 0. Now, we like 0, and that's a really important idea. When possible, try to get 0 into your computations. And in general, sooner the better. Which means that as soon as you can get 0 involved, try to do it. So we like to get 0 inside as much as possible. Now you might say, why do you care so much about 0 being showing up early? Because oftentimes when you evaluate at 0, what happens? Well, things go away. That's why we like 0, because 0 is a great simplifier. And so this is a piece of advice. Now, if you chose to do things horizontal, perfectly fine. You would still get the same answer, but I suspect it would be a little bit trickier. So let's finish it vertical, and then let's talk about maybe what would have happened if we had gone horizontal. Okay, so if we're thinking about vertical slicing, then that really says our order of integration is dy dx. Okay, so we say, where does x go from? Well, lowest value of x to the highest value of x, 0 up to 2. Where does y go from? Well, goes from here, right, y equals 0, up to y equals x, 0 to x. Okay, so we get integral 0 to 2. Integrating this with respect to y is very easy. You end up with 2y over 1 plus x squared. And evaluate from y equals 0 to y equals x. Now, notice you plug in 0, you get 0. Plug in x, you'll get 2x upstairs. So integral 0 to 2 of 2x over 1 plus x squared dx. That's the power of 0. See, when you plugged in 0, it simplified dramatically. Woohoo! We like that. Now, how do you integrate this? Well, that's not so bad, because what do you see? The function 1 plus x squared downstairs, if you take the derivative, you get the upstairs, 2x dx. So it's the derivative over a function, which means the antiderivative of this is the log of 1 plus x squared. And you evaluate 0 to 2. When you plug in 2, you'll get log of 1 plus 4, which is log of 5. When you plug in 0, log of 1 is 0. So there's our answer, log of 5. And you're probably thinking, wow, Steve, this is so unlike you. Where are your arctangents? I've come to expect more. Well, I'm sorry. Now, that is if we had gone and integrated things in the setup where we did our vertical slicing. If we had gone horizontal, okay, sure, we could have done that. Well, it'd be integral, same function, dx, dy. Now, where does y go from? Well, lowest value of y to highest value of y, still 0 to 2. All right, that's not so bad. How about x? Well, it goes from x equals y to x equals 2. So it goes y to 2. So, now what? Well, that comes integral 0 to 2, and that's an integral we know how to do, 2 arctangent of x, evaluate from x equals y to x equals 2 dy. And that would be the integral 0 to 2 of 2 arctangent of 2, right, because that's, plug it in, subtract 2 arctangent of y dy. And now we're like, okay, the first thing, that's not so bad. That's integration of a constant. We can do that. Integral of arctangent y. It's possible. We have the technology, but it's not obvious. And it's not one of those things we have memorized right at the top of our heads. Somehow you might think, well, don't we have it memorized by now? You'd have to do by parts to go and make progress. And this would be a little bit trickier. So a little bit of a ugh. But if you did opt to do that, and I'm going to skip the steps, I'll let you work it out. But if you did opt to do that, lo and behold, you would get the exact same answer. But it would take you a little bit longer to do it. All right. Well, good. What a fun problem. All right, well, let's keep going. More fun problems to do. So here we go. Let R be the region y less than or equal to x squared and 0 less than or equal to x less than or equal to 2 minus y squared. And we want to write the integral f of xy dA as iterated integrals. Okay, all right. Well, let's see what the picture is. So we have y is less than or equal to x squared. Okay, so we should start here, graph some things. We're below x squared. Okay, so I'm going to dot in, here we go, with x squared. All right, and then we also have that x is greater than or equal to 0, great, and less than or equal to 2 minus y squared. Now, we have to think about this. X equals y squared would be a parabola that opens to the right. Minus y squared would make it open to the left. The 2 shifts it over. So what ends up happening is it comes out here over to 2, and I'm going to mark this as y equals x squared, and then we have parabola coming up here, and coming down here. All right, so here we go. What is the shape? Well, we've got to be below x squared, so we need to be underneath y equals x squared. Okay, that's good. We've got to be greater than or equal to 0, which means we have to be to the right, and we've got to be to the left of 2 minus y squared. So our shape is that region there. Let me highlight it here. All right. There we go. There's our shape. What a fun, interesting region. It's kind of like you have a parabola, but then you sort of bit a little piece out of it in the corner. All right, great. Well, what do we do? Well, we have to make some decisions, right? We have to decide on how we integrate. The other thing we should probably do is label. So when we talk about labeling, we mean let's label the curves. Some of them are pretty easy. X equals 0, that's pretty easy. We know this is y equals x squared, but we should label it both ways. So y is a function of x, yes, but also x is a function of y. X is square root of y. How about this corner? Can we find that? What would be true? Well, if we're in this corner, what would be true is that we'd have to have x squared, y equals x squared, and simultaneously x equals 2 minus y squared. Wow. Okay. Well, let's think about that for a second. Let's finish labeling things. So here we have x equals 2 minus y squared. Now, note that you could have said, oh, this is y squared equals 2 minus x. So we could have also written this as y equals the square root of 2 minus x for the top part, and y equals minus square root of 2 minus x for the bottom part. Okay, so this intersection. Okay, now one way you can do it is guessing, which is not so bad. So let's see, can we think of a nice pair of numbers, right? Because this is a coordinate, something comma something, where if we square the x, we get y, or if we square y and subtract it from 2, we get x. I can think of one. Actually, I can think of 1 and 1. Right? 1, 1. Now, if you don't like that, you could say, okay, here, let's just think of substituting. So when does y squared equal 2 minus x intersect y equals x squared? Well, you can substitute in, right? So replace y by x squared. That's the same as when does x to the fourth equal 2 minus x. And then we just do some factoring, right? Well, it's maybe not the easiest factoring, but yeah, you can factor it, and you'll get some answers. One of the things you can do is look for reasonable roots, and the only reasonable roots here are at 1, minus 1, 2, and minus 2. But that's, we're getting sidetracked, so let's continue on. So everything here has been marked. What we have to decide now is the order of integration. Or put another way, are we going to do things vertically or horizontally? And we can do both, because it says, it doesn't specify which one, so maybe we should do both. So let's suppose we start with vertical. I do think vertical slicing is a little bit more intuitive for most people, because they like to think of y as a function of x, and that tends to happen with the vertical slicing. So if you just sort of sketch, you'll notice that something happens at this point here. What do you see happening? The top curve changes. Well, what does that mean? It means we're going to have to do two integrals. So every time we have a change in the bounding curve, we have to split up the integral. All right, so if we're integrating with respect to the order dy dx, what will happen? Well, so we're going to have two pieces, integral, integral, f of xy dy dx. Now this first piece, we can go from where we start to our first transition point. Well, in this case, there's only one transition point. So we start at 0, go to 1, and then we do what? Well, we go from the bottom to the top. So the bottom curve is minus root 2 minus x, because we're thinking this as y. So we have y equals, so that's why it's minus square root 2 minus x. Top is x squared. Add to that integral, integral, f of xy dy dx. Now, from here, we're going from 1 to 2. So 1 to 2. And we're going to go from the bottom to the top. The bottom curve, minus square root 2 minus x. The top curve is plus the square root of 2 minus x. That's it. That's it. Great. That's one answer. Now, if we did it the other way, dx dy, what would we end up with? Okay, now, here, we're doing our vertical. Sorry, excuse me, horizontal. My hand was in the right phrase, right? And kind of reminds me, there was an old TV show called The Outer Limits, said, we control the vertical and the horizontal. Okay, so we look, we say, okay, as we do our horizontal slicing, something interesting happens halfway through. Namely, this curve on the left transitions. So we're going to have to do two integrals, because every time that there is a change, we have to figure out what's going on. All right, now one thing we haven't marked is where is this point at? So let's figure that out. Well, that would correspond to what? Well, it's x equals 0, because I'm here. So if you plug in x equals 0, this is at minus root 2. So here we go. We're going to have integral, integral, and our function f of xy dy dx. Now we go from the starting point, low point, minus root 2, up to as far as we can go with the same curve. So that's to where we transition, which would be the x-axis, which is at y equals 0. So minus root 2 up to 0. And then we're going to have from the left to the right, low value to high value. And, whoops, I wrote dy dx here. This is dx dy. I'm sorry about that. There we go. So we're going to go x equals to x equals. So we're going to have x equals 0 to x equals 2 minus y squared. So 0 to 2 minus y squared. Plus, okay, integral, integral. It's always going to be integral, integral, right? Because it's a double integral. Dx dy. And now, okay, we're going to go from where we stopped. We stopped at 0, so we're going from 0 up to, in this case, up to the end. So the highest point is up here. That's y equals 1. 0 up to 1. And now, left to right. Low value to high value. X equals root y. X equals 2 minus y squared. So square root of y up to 2 minus y squared. That's it. We're done. Aha! All right, good. Well, yeah, you look at these two things and you're like, wow, how could they possibly be the same? But then you dig into it, it's like, oh, okay, yeah, you really have the same region described in multiple ways. So it's good to be able to do that. All right, well, let's keep going. More to do. More to do. Okay. Let R be the region in the first quadrant bounded by x equals 0, y equals 0, and the ellipse 4x squared plus y squared equals 4. Find the integral over the region x plus 2y dA. All right. Well, let's sketch this. What do we see? Well, we have some bounding curves. We have, of course, y equals 0. That's our x-axis. We have x equals 0. That's our y-axis. 4x squared plus y squared equals 4. It tells us it's an ellipse. We can actually figure some things out. For instance, where does it hit the x-axis? Well, if I'm on the x-axis, y equals 0, 4x squared equals 4, which says it'll hit it here at 1. Where do I hit the y-axis? Well, that's x equals 0, y squared equals 4, which means it'll hit at 2. So this is at 1, this is at 2, and so we have our ellipse. So it's a circle that's kind of been stretched vertically. Okay, so there's our region. All right, well, that's interesting, fun region. And, okay. Well, what's the expression? Now, in some sense, we have to make a decision. Do we think it's easier to integrate with respect to x or with respect to y? I don't think either of them have a clear advantage here. Because look at what we have here. We have, they both functions look more or less the same, x and y. And the function here, essentially there's an x squared, there's a y squared. There's so much symmetry that there's not bias one to the other. So if I have no reason to prefer one to the other, I tend to slice vertically just because I'm used to, and years of indoctrination, I suppose, has done this, thinking of y as a function of x. So suppose we think about slicing vertically. So we solve for y. Well, what does that say? Y squared is 4 minus 4x squared. And so we take the square root. We just need the positive part. And we can pull out a 4 also, because see, this is the same as 4 times 1 minus x squared. So when you take the square root of 2, square root 1 minus x squared. So that's why we say, oh, it really is like a circle that's just been stretched by a factor of 2. All right, well, let's set up our integral, and let's do some integration, and hopefully we get an answer. Well, we'll get an answer. Hopefully it'll be a nice answer, because we like nice answers. We work hard. We should get some nice answers out. Okay, so we're integrating x plus 2y and dy dx. Vertical slicing. Well, where does x go from? Well, lowest value of x to the highest value of x. We're going from 0 up to 1. All right, that's not so bad. How about y? Well, we're going to go from this bottom curve, y equals 0, to this top curve, y equals 2 square root of 1 minus x squared. 0 to root 1 minus x squared. Yep, that's what you do. So, when we integrate, what does this become? Integral 0 to 1, and integrating with respect to y would be x times y plus y squared. And we're going to evaluate y equals 0. Oh, that's nice. I like y equals 0. It's going to be pleasant. Y equals 2 square root 1 minus x squared. Okay. All right, well, we'll work with that. So let's see, what do we have? This will become integral 0 to 1. We substitute, again, when we plug in 0, we're going to get 0, so we just need to plug in the top bound, right? So we'll have x times 2 square root 1 minus x squared. We can write that as 2x square root 1 minus x squared. And then plus y squared, well, that'll be the square of that, which is the same as 4 times 1 minus x squared. All right, good, dx. Now, we can break this into two integrals. So if we wanted to, we can say, look, the first integral it feels like it's going to be something different than the second piece, right? The first piece feels maybe like there's a substitution coming up. The second piece feels like, hey, there's no problem with this integral, let's just do it. And so we are allowed to split things into parts whenever we have addition and subtraction, and whenever we feel like, oh, we might have different behaviors depending upon which part we're doing. So for the first part here, we say, hey, derivative of x squared is like 2x, so we can do a quick substitution. U equals 1 minus x squared. du would be minus 2x dx. And so this would become the integral. 1 minus 0 squared, 1. 1 minus 1 squared, 0. Now the 2x dx, well, there's not a minus there, so we'll put a minus. So that's minus du. And then the square root of 1 minus x squared is u to the half. Well, okay, we can clean it up. We can swap the bounds, get rid of the minus. So this is really the same as integral 0 to 1 of u to the 1/2 du. Well, that's 2/3 u to the 3/2 evaluate from 0 to 1, which would give us 2/3. All right, great. We can work with that. It's a lovely thing to work with. Okay, so the first integral turns out to be 2/3. All right, so we have 2/3. And then plus, well, we still have to do this integral. Okay, what will that be? Well, 4 times x minus 4/3 x cubed. And we're going to evaluate 0 to 1. And, well, when you plug in 0, you get 0. And so plug in 1. So we end up with 2/3 plus 4. Well, we can write that as 12/3 minus 4/3. Okay, well, 2/3 plus 12/3 minus 4/3 leaves us with 10/3. That's it. Woohoo! Another problem done. Yes! And actually it wasn't so bad. You might have been like, oh, there's a square root. It's going to be terrible. But then I was like, oh, this isn't so bad at all. This is stuff we can do. Wow, fun. Good stuff. Fun problem. Well, keep the fun coming. On to our next problem. All right. Evaluate the integral -1 to 0, integral 0 to 1, cosine of y cubed plus y, dy dx, plus integral 0 to 3, integral root x over 3 to 1, cosine of y cubed plus y, dy dx. And whoa, all right, well, what do we do? Now, one thing we can spot is, hey, these functions are the same function. It's cosine of y cubed plus y in both cases. All right, well, if that's the situation, if they're the same function, it stands to reason that what we should do is somehow do them together. So we should mush these two integrals into one integral. All right, well, if we want to be doing a mushing here, we should really think about how can we combine them. There's one other thing going on here, which is we don't know how to integrate this, right? Cosine y cubed plus y, integrate that with respect to y, hopeless, hopeless. Forget it. We're not going to succeed. But if we change the order of integration, so we integrate with respect to x, mildly hopeful. Mildly. All right, so let's start by understanding our region, because we're going to have to change our order of integration. Now, for the first integral, it's not so bad. We can actually read off what's going on, right? Because it says, look at what x does. It says -1 less than or equal to x less than or equal to 0, and then y goes 0 less than or equal to y less than or equal to 1, which means it's a nice little square. And in particular, it's the square. Here's -1, here's +1. There's our square. All right, so that's our first integral. Okay, wonderful. Okay, but that's the first piece. What about the second integral? That's a little bit more interesting. Okay, let's work on that one then. Okay, so what do we have? We have the outer bounds tell us x goes from 0 to 3. Then the inner bounds says square root of x over 3 is less than or equal to y, less than or equal to 1. All right, now y equals 1, we can sketch that. It's very easy to sketch. It's just a flat line. The other curve, a little bit more tricky. Well, what is it? It's a square root of x over 3. Well, okay, the square root of x over 3 is just basically like a square root, but kind of scaled. Where would the square root of x over 3 hit 1? In other words, if we're thinking of these as curves, y is a function of x. Where does y equals square root of x over 3 intersect with y equals 1? Well, that would happen when x over 3 was 1, which happens at 3. All right, so we can imagine we come out here to 3, and so what we're seeing here is something that looks like a square root curve, so just a little bit down. So this is y equals the square root of x over 3. So our second integral, in terms of where we're integrating over, it actually fits sort of nicely next to our first integral. So there we go. There's our basic shape. Cool. All right. Well, now we have our region. We're ready to change the order of integration. So where do we go from here? We can say, the nice thing about, notice, because we're doing, see, both of these, currently dy dx, it's all vertical. And we have to do two integrals because we have a change in this bounding curve for the lower part. Whenever we have a change in the bounding curve, we got to split it up. But when we think about going dx dy, we're doing our horizontal slicing, it's one integral. So that's fantastic. It feels like we're cutting our work in half because we're not going to have to do two pieces, it's just one. So integral, integral, same function. We don't change the function. We're just changing the order, dx dy. Well, all right, let's work on the bounds. Where does y go from? Low value of y to high value of y. Well, we can see 0 to 1. All right, that wasn't so bad. Now, where does x go from? Well, we're going to go from the left-hand side, which corresponds to x equals -1, out to this curve. Now, currently it says y is a function of x, but we need to get it as x is a function of y. These are x bound, so I'm going from x equals something to x equals something. Squaring both sides here, we can say, look, that's the same as y squared equals x over 3, or we can say x equals 3y squared. So from -1 up to 3y squared. All right, well, great. We've now changed our problem by changing our order of integration. It's one term, and let's proceed. So integral 0 to 1. When we integrate this with respect to x, no problem. Cosine y cubed plus y acts as a constant, so I have x. Evaluate that from x equals -1, x equals 3y squared dy. Well, that would be what? 0 to 1 cosine y cubed plus y. And now we have 3y squared subtract -1. Well, subtract -1 is +1. And now we say, okay, that's the integral we have to do. Now, previously we said cosine y cubed plus y, hopeless, hopeless. But now we have, oh, there's some extra stuff in here. Is there any hope? I think there is, because notice if you take the derivative here, so if you think of this as u, this part is du. So now we're like, wonderful. So let's actually do this computation. So u is y cubed plus y. What would our bounds be? Well, 0 cubed plus 0, 0. 1 cubed plus 1, 2. And we have cosine u du. And the integral of cosine is sine. So sine of u, evaluate from 0 to 2, plug that in, get sine of 2 minus sine of 0, which is 0. And so we have sine of 2, which is also, that's right, it's sine of 2. Yeah, you can't simplify sine of 2. But that's okay. We don't have to. That's our answer. Wow. Wow. What a great answer. It actually turned out to be pretty nice at the end. Well, of course, these problems were chosen so that they'll be nice at the end. Maybe not the most surprising thing that things worked out nicely. But it's still a nice thing. We like it when things work out nicely. We love it when a plan comes together. One more problem. One more problem. Here we go. By changing the order of integration, write the following as a single integral. One integral. So we want to find one integral to rule them all. One integral to find them. One integral to bring them all. And in the light of multivariable calculus, bind them. Yes, that's what we want. Good. Okay. So we just have to write it as a single integral because we can't integrate. We don't know what the function is, but that's all right. So what we're going to do is just work through it piece by piece. We have 3 parts, and once we see the geometry for each part, we'll see how they all fit together, and it looks like we'll end up with a single integral at the end. So let's work our way through it here. All right, so we're going to get a sketch going here. Okay, so, well, let's begin at the first one, right? So let's talk about the first one. So in the first one, what happens? Well, we're told x goes -1 to 0. And then y does what? Well, we go from 0 up to 3 plus 3x. Now, okay, so -1 to 0, so we should come over here, -1 to 0, and then y equals 0, that's easy to spot. The other thing that is helpful, we see y equals 3 plus 3x, and we say, okay, we just need to know what happens at -1 and what happens at 0. Okay, plug in -1, 3 plus -3 is 0. Oh, so the line passes through that point. Plug in 0, 3 plus 0 is 3. So, okay, so here's 3. So it's this line here. So that's our first piece is that triangle. All right, one piece down. Okay, well, more to do, right? Okay, let's talk about our second piece. So what's happening with our second piece? Well, it's actually really clean, right? Look, what does it say about x? X goes 0 to 1, and y 0 to 3. All the constants, all the bounds are constants, which means rectangle. So we go up to 1 in the x direction, and up to 3 in the y direction. And, all right. And so there we go. There's our second integral. Okay, great. Ha! 2 down, 1 to go. So our last piece. Well, okay, our third integral. Well, what will that be? We have 1 less than or equal to x less than or equal to 2. That's the outer layer, tells us. The inner layer, x squared minus 1 less than or equal to y less than or equal to 3. Okay, so the top is still 3. That's great. And we're only going up to 2. And we see, hey, this is a parabola of some sort. But it helps just to say, okay, just think about what's happening. If I want to sketch it, I just know it's a parabola opening up. And I just need to know what's happening at 1 and 2. And then just say, well, connect it like a parabola-like line. When I plug in 1, 1 squared minus 1 is 0. So it's going to hit there. When we plug in 2, 2 squared minus 1 is 3. So it hits there. So it's a parabola that will pass through those 2 points. So it's not a line. There's a bit of a curve to it. So I'm going to make a note here. This is y equals x squared minus 1. And again, we're doing our vertical slicing. And you can see why we had to split it up. Because as we transition between the three different places, there was a change in either the top or bottom. See, here we changed the top curve. And here we changed the bottom curve. Every time there's a change in the curve, there has to be a transition. Now we should have, and we'll do it right now, also have marked that this line on this side is the line y equals 3 plus 3x. All right, well, we're almost done because the picture is going to give away what we need to do. Well, what's going to happen? Instead of going vertical slicing, time for horizontal slicing. All right, okay, we can do that. Horizontal slicing we go. Doom, doom, doom. And notice, as we go horizontal slicing over this region, we always have a consistent left hand and right hand side, which means we only need one integral, which is good, because we only wanted one integral. If we needed like 5 integrals, we'd be like, ah! But we're good to go. Progress can be made. Okay, so what do we need to do? We need to figure out these curves here as x as a function of y. So for instance, if you divide by 3, you have a third y equals 1 plus x. Or if you subtract 1 then, we could say, hey, this is the same as x equals 1/3 y minus 1. Here we can add 1 to both sides. Y plus 1 equals x squared. Then take the square root, knowing that we want the positive square root because x is positive in this part. And we say, x equals the square root of y plus 1. And now we're ready to write it down. Integral f of x, y, dx, dy. And we say, all right, where does y go from? Low value to high value. Low value, 0. High value, 3. So 0 up to 3. X goes left to right. Low value to high value. Low value as a function of x, right? Because these are x bound, so x equals. So we go 1/3 y minus 1 to the high value, square root y plus 1. That's it. We're done. Great, fun, wonderful, woohoo, yay! So not so bad. It's just a matter of being patient, drawing a picture, figuring out what do the bounds mean, and being able to say, okay, how do I find the new bounds? Which of course is practice, practice, practice. We're going to be doing more integrals. We're going to be doing more practice. Keep it up. It'll soon become more natural. And then you'll start to say, the process is, other than understanding there's a geometrical picture, it's not so bad. You might even start to enjoy it a little bit. We hope so. All right, thanks for coming. Hope to see you again. Bye.